So again, back in here, if you take a look at this in here, in the frame in here, in the frame transmitted in the second layer, which is the data link layer, there is two sublayers: the MAC, media access control, and the logical link layer. All right. So the function of the media access control is to make sure only one transmission at one time. If there's two transmissions, that will cause collision, and collision will corrupt all the transmission. So let's take a look at the MAC, the media access control. All right. So I hope the concept is clear for you. So look in here. Let's see. This is a wire, right? Let's say a hub, and you have four nodes: node A, B, C, and D. And at one time, only one communication should happen between A and B, A and C, C and B, B and D. Doesn't make a difference. All right. So let's say in here, let's say that B. Okay, transmit a packet. So B starts at time T1. In here T1. So the packet, the transmission will go this way and will go this way, right? In the wire. It'll go this way and will go this way. And because there's a delay, that's why we see the line goes like this down. There's a delay. There's a propagation delay. Think about like, you have a hose and you open the water source, all right? So the water to go to the end, it has to propagate, right? You don't see the water right away. The same thing, when the signal is moving from node B to node A, it's gonna need some time, all right, some time in here. So it's gonna go and eventually will reach A. And the data, when it goes this direction, it's gonna need some time to reach node C, for example, right? And let's say at time 2, okay, C sent a packet, so the packet will go this way and will go this way. All right. So because the transmission of B did not finish before T2, T1 happened in here, the data is still going, all right? And then some point of time before this transmission ends, C sent a packet, all right, in here. Then now from all of this time in here, there was what? Both signals exist. So this signal will mix with the other signal, and that's what we call it collision of the data. Okay, all right. So this is where is the area where B signal exists, and in here area where is A signal exists. All right. So that will cause collision. All right. So we have to prevent collision. All right. We have to prevent collision. That means should be one communication at the one time. It's exactly like we now think about our lecture in here, like this wire in here. All right. If two people talk at the same time, what will happen with your voice? Your voice is a signal transmitted over the air. What will happen to the signal? They will collide. Then I will not understand anything. Right? That's what will happen. The same thing is happening here. So we have to apply something called common signal CSMA um, common signal multiple access. Common signal multiple access. Where in the media we'll have multiple access, so we have to create a protocol in here to control the whole process, and that's the job of the MAC. Okay, media access control. So it will control who has or who will have access to the media, to the medium in this case. Clear? That's a function of the MAC. All right. So in here, so we have to apply something called collision detection. Okay, collision detection. All right. So when there is a collision, it needs to stop. Both has to stop transmitting and try at the other time. So again in here, okay, A starts at time T1. All right. Transmission time, it will take until T4. So the data supposedly to go from T1 all the way to here. At the same time, D4 send the data at T2 and ends at T3. So as you see in here, they collide in here. So C detects a collision because there's two signals in here, right? All right, two signals. It will detect a collision and upwards. All right, and at this time in here, A detects a collision and upwards. All right, so when there's a collision, both of them will upwards, will stop sending because there is no point. The data is garbled; they are mixed together, and that's what we call it collision. CD for collision detection. So it's like you detect a collision. Once you have a collision, stop from sending further data. Clear? So the mechanism applied in Ethernet is called collision. It's called collision detection, CD, or collision detection, and that's in the standard Ethernet. All right, in the original Ethernet, which is like 10 megabits per second. Okay, now it's rarely used, but that's how it works. And again, the carrier sense multiple access collision detection is the protocol used to avoid the collision. All right, so so in the standard Ethernet, if the maximum propagation time is 25.6 microseconds. Propagation time, what is propagation time? Let me go back in here. So when the data, okay, goes from here to here, okay, there's a propagation time. That's the maximum propagation time, okay, is the time from sending to the time of receiving. Okay, that's propagation time. So usually in the Ethernet, the maximum propagation time is that much, 28.6 microsecond. Okay, if that's the case, what is the minimum size of the frame? What should be the minimum size of the frame? What we are trying to tell you here, remember when we went back in here, let me go back all the way. Okay, just
64.
okay, 64. It's not in this, it's in the other presentation. It was 64 bytes. All right, just we need to know where's the 64 bytes coming from. Got it? So it's 64 bytes. So where is it coming from? So this is the propagation time, 25.6 microsecond. So the frame transmission time is the frame transmission time for frame transmission equals 2 times the propagation, because it's gonna go one way and come the other way, right? Okay, so the TP, which is 25.6 microsecond, you multiply them together, the transmission, the frame transmission time will be 51.2 microsecond. So that means in the worst case, a station needs to transmit for a period of 51.2 microsecond to detect a collision. All right, because there is a frame will be sent and acknowledgement gonna come back. All right, so you need a time to send and time to come back. That means the minimum size of the frame at that speed, which is 10 megabits per second, multiplied by 51.2 microsecond, that means 512 bits or 64 bytes. So we should not allow the frame to be less than 64 bytes. That's where the 64 bytes coming from. Okay, that's where it's coming from in the Ethernet. All right. So it's a mathematical calculation, and that's why if it's less than this number, we do padding. We do padding. Padding is like adding bits to it to make sure it's like a 64 byte. So let's take a look how the carrier sense multiple axis collision detection work. This is the flow diagram. All right. So K is the number of attempts. If you try to send a packet and there's a collision, you stop and you try again. Second attempt, then a third attempt, then fourth attempt. All right. And the maximum number of attempts are 15. okay, from 0 to 14. All right. So at the beginning, at the first attempt, the number of the attempt is 0. You agree? All right. So you attempt to send it, and gonna come in here. The first thing what you will do, you will check if the channel is free. Okay, how you check if the channel is free? Okay, by listening to the channel, the ether. Is there a transmission? Okay, there's no transmission. Then the channel is free. You're good. All right. If it's false, you're gonna wait. False, you're gonna wait. If it's true, that means the channel is free. All right. Okay, what you have to do now, you're gonna go to this box in here. Okay, and okay, is it done or there is a collision? All right. If there is a collision, if it's done or done or there is a collision, that you know that there is a collision. It's true. There is a collision. All right. You're gonna go to the next check. Okay. Detection collected, collision detected. If there's a collision detected, what you have to do, you have to send a jamming signal. What does the jamming signal does? Tells everybody in the network that there's a collision. So you help everybody to know that there's a collision. So you send a jamming signal. You jam everybody from sending. Then the trial will be encrypted by 1. So you started by trial number 0. Now will be 0 plus 1. This is attempt number 1. The next one will be 1. All right. Is the attempt less than 15? You still have a chance. Go. If not, then abort. Then you go back in here. Then you create a random number R, which is a random number 0 to 2 to the power k minus 1, a random number. All right. And then you wait for time b seconds, the back off time. How you calculate the back off time? So when you have a collision, you don't go right away and you try. If you go right away and try, okay, still maybe a collision, maybe another collision. So what you have to do, you have to have a back off time. All right. So how is it calculated? By a random number times the TFR, okay, which is the frame average transmission time. That's the time you're gonna wait. All right. After the time is wait, you gotta go back to the whole beginning now. K now is 0, and you try again. And your goal, you have to go through path. If there's a collision, you're gonna go repeat the second try. If there is a collision, you try the third trial, the fourth, the fifth. All right. If you go to 15, then it has to be dropped. All right. Now, if the channel is a free, all right, and done, you finish the transmission. All right. Finished transmission is done. True. Then you're gonna go in here. Is there a collision? No collision. False. Okay. Then it's successful. All right. So you need to go from here to here. If there's a collision, you're gonna circle, try it again. And every time you'll wait different amount of time because there is R, a random number, and there is a factor how to calculate the number. So maybe the first time you waited for 5 seconds. The second time there is a collision, you wait for 10 seconds. Fourth time for again 3 seconds, and so on and so forth, until the process is complete. And that's what is carrier sense. What is carrier sense? What is carrier is the medium, because the media carry the signal. Sense. What is sense? Because each node try to sense, is there a collision? Is the channel free? If it's a free, you're gonna go sense. Multiple access. Why is it multiple access? Because multiple nodes, multiple computer, multiple hosts have access to the media. So carrier sense, multiple access, slash CD. Why is CD? Because you try to have collision detection. Once there is a collision detection, stop, send a jam signal, and try again. Okay, wait for a while, try again, until then. So that's exactly how carrier sense multiple access CD works. That's exactly how it works. All right. So moving on. So this is summary of standard Ethernet implementations. All right. So uh, Taking a look at the characteristics, okay, okay, first of all, the technologies are 10 base 5, all right? Let's just start with a 10 base T. 10 base T that everybody of us know and use every day. It's like the Cat 5 cable, you have it in your home. Your computer now is connected to router or to the switch, right? Okay, it's 10 base T, 10 base T, and it used two and shielded a twisted pair. We call them a twisted pair. Why we call them a twisted pair? If you peel the wire, if you peel it, the wire, you'll see 8 wires and they are twisted together. Okay, twisted. And why they are twisted? To reduce noise, to take the noise away. Okay, to take the noise away. All right. So this, the one we all have it. If you look right now at the back of your computer, if you are connected to the router, you'll be able to see it, right? In the labs, everywhere you see it. Okay. The maximum distance for the wire is 100 meter. It cannot be longer than 100 meter. All right. So that's everybody knows. The other one all of you know and have seen before is the 10 base 2. 10 base 2, and we call it thin coax, thin coax. The thin coax is like the TV cable. If you have a TV cable, it's like plugged to your TV, that a thin net or coax cable. And when I started knowing the network in early 90s, 88, 90s, I was baby at that time, that was the most common media before the cat files, right? And the nice thing about it, you could have up to 185 meters, so it's a longer distance. There's a coax cable, but thick. It's thick. You see, the one at your home behind the TV is thin. There's another one, thick coax cable, which could be 500 meters. To be honest with you, I never seen it myself. I see it like on the in the books, but I never worked with it before. And this they call it 10 base 5. To remember where's the 5 coming from, because the range is 200 meter. Okay, to remember the 2 in here because it's almost 200 meters in here. That's where the 2 coming. Okay, and 10 base T, where is the T coming from? The word twisted, because we used N shield twisted pair. All right, then something we don't see it a lot in the houses to the endpoints. We don't see the 10 base F, which is like a fiber. The fiber, you could, I mean, you could have a fiber, Ethernet card and you plug a fiber, but usually you don't use it for the endpoint, maybe to connect a switch to switch or router to router or so. So this could be like 2,000 meters, 2,000 meters, and that's the nice thing about the fiber, that you could transmit data for longer distances. Clear? So in here the standard Ethernet implementation. And here the 10 base 5, which is the thick net coax cable, 500 meter. It looks like that. It looks like this in here. Uh, all right. Okay. And then, okay. And usually we have a tab, so we connect the computer through a tab. Again, myself, I did not use it much. I never tried it. I use this. So in here is thin coax cable, like the TV wire. The range 185, and we call it 10 base 2. Again, 2 because this is almost like 200. All right. And usually we have a T. If you remember, if you are old, there is a T. So T connects one side, connect to the computer, and they will be in series like this. And by the end in here, we have something called terminators. Terminator 25 ohm terminators. In here we'll find 50 ohm terminators. Anyways, these are all technologies. I don't think you will ever see them again. Okay, just know about them. Then we have, now we don't use like computers in series like that. Now we use a hub. Okay, a hub or a switch. As you see in here, it's like a phone jack. This is not a phone jack. Okay, it's RJ45. Okay, and it's an unshielded twisted pair. okay, it will connect. You're gonna use four wires, and they are connected to your computer as you see in here. And of course, you'll have the fiber. I mean, the fiber you could. I mean, nobody use fiber to the endpoint. It could, but I didn't. It's not very common. Very expensive, first of all. But it's like two optic, one for send and one for receive. They will be connected to a fiber Ethernet in your computer, and they will be connected to a fiber port in here. All right. So these are the standard Ethernet implementations. So the summary of fast Ethernet implementation. So these in here are the standard Ethernet, right? Let me refresh your memory. In here, remember we said standard Ethernet, then fast Ethernet, then gigabit Ethernet, 10 gig. So we finished the standard. Let's now go to the fast Ethernet technology. And the standard Ethernet also is gone. I mean, nobody uses standard Ethernet anymore, right? So yeah. So now we'll go to the summary of the fast Ethernet implementations. So what you have the 100. So 100 coming from where? 100 megabits per second. This is speed. Base. So you have the TX, which use a shield twisted pair. Shield, not UTP is S. Shield twisted pair. The number of wires too, and the maximum length again is 100 meters. So the segment maximum is 100 meters. Then you have the 100 base FX, F usually for fiber, FX, which is fiber, to the wires, and again it's 100 meters. And then you have the 100 base T4, okay, T4. And this is the most common one, which is unshielded twisted pair, 4 pairs and 100 meter. So the most common one among these in here is this one, the 100 base T4, using unshielded twisted pair. All right. So again, this is an example. This is the most common one we said, and that's exactly right now. If you look, that's exactly what we have all of us when we are connected to the switches in our houses. Okay, we have the 100 base T4 hub and are connected 4 pairs of wires. Okay, that means 8 wires for each node connected. All right. There is the fiber one, and there's also the shield twisted pair. Myself, I have never seen this. I seen this with this once, but this is what we see every day in here. All right, then yes.
For the ones that are connected to hubs, do they not need the carrier sense?
They are no. I mean, the new technology does not use the carrier sense. I mean,
Okay.
the standard use the carrier sense. Okay. All right, because the new technology it's like full duplex. There is one transmission, one for send, one for reception. We'll talk about it. Then the third one, if you remember the summary of the gigabit Ethernet implementations, all right, this is you'll find it mostly in the infrastructure, all right. So the thousand coming from where? From the gig, using the gig 1000 base SX, all right, and this is fiber shortwave, and the maximum distance 550 meters. Then 1000 base LX. Remember the cars when you buy cars, they tell you SX, LT, whatever, all of that. So it's like okay, limited, whatever. So the fiber long wave is 5,000 meters. Then you have the 1000 base CX. This is shielded twisted pair, which is 25 meters, and then the 1000 base T4, which is the Cat5 and shielded twisted pair. This is the most common one that is used, right? Okay, the gigabit is the most common one. All right. So in the full duplex mode of gigabit Ethernet, there is no collision. All right. For the person asked me, there is no collision. The maximum length of the cable is determined by the signal attenuation in the cable. So the signal, when it travels further, it will get attenuated. So that's how you determine the maximum length. All right. All right. So then after that we have the gigabit. This is the images for the gigabit we just saw here and here. And again, this is the most common one that we might have in our houses, like the gigabit, right? And here is the CX, the LX, and the SX, different formats. Then we have the 10 gigabit Ethernet implementation. There is the 10G base S, 10G base L, 10G base E. All right. And all of these are fiber. You know, when you go to the 10 gig, it's not anymore a twisted pair. Okay, it's all fiber. So this is multi-mode, and the fiber, there's two types. There's a multi-mode fiber and single mode fiber. Usually the single mode fiber, they go further distances. So look at the 10G base E in here, single mode fiber. It could connect 40,000 meters, 40 kilometers. 40 kilometers is like about how much? Like divided by 1.6, it's like 25 miles, 25,000 miles, 25,000 miles in one wire. Okay, 25,000 miles in one wire. And then you have the 10GL, 10,000 meters, and that's why you connect state to state with this technology, with the fiber, with this technology. All right, let's hop on to the wireless LANs. So wireless communication. All of us are using Wi-Fi, the IEEE 802.11 wireless LAN. Okay, this is the Wi-Fi that we use. Okay, and also, and this is what they call it, wireless Ethernet also. Okay, anything which starts with 802, then it's an Ethernet. All right, Ethernet. All right, so we have the Bluetooth, was also wireless, that it's used a lot, and you know there's other technologies could be used. So um, um, let's take a look in here. So the first network is called the Basic Surface Sets, BSS, BSS. So in here you have four computers. Each one will have like a wireless card, and they will be able to communicate with ad hoc network. So there is no wires, okay? There is no switch in between them. There is no hop in between them, all right? They are connected using this using using the air. They're transmitting using the air. They are forming ad hoc network, and this is a BSS without access point, all right? You could have infrastructure BSS with access point, all right? So you have an access point and you have node. So in here, if this station wants to communicate with this station, it will send the signal directly. There's no problem. In here, the access point is the connector. So there is no direct communication between the station and the station. So the station will send the data to the access point, and the access point will send it out to the destination. So the access point is uh, the in the middle to do the connection. Then bigger than the BSS, so we start with the BSS, which is basic surface sets. Then we'll come to extended surface sets, ESS. All right. So in the ESS, the same thing. You'll have a BSS, and we have another BSS, a third BSS, all of them interconnected to a switch here, okay, and then we connect it to a server or a gateway. So this, when you have, multiple BSSs will be connected in one ESS, okay, which is extended surface set, and the BSS again is the basic surface set, and this is the AP is the access point. And all of you know what's access point. If you go to the school or Walmart or anywhere, you look in the ceiling, you'll see the access point, or your house. When you have the access point, you use the house. Now, okay, what is this technology? It's Ethernet, still Ethernet, right? IEEE 808 is an Ethernet, right? But you know, we cannot use the CD, collision detection. Why? Because there is no medium. When it's in a wire network, the data goes through the medium. So you could use collision detection. Here you cannot use collision detection. You have to use different technique, which is called collision avoidance, CA, collision avoidance. So you have to avoid the collision. Okay, so it's again carrier sense multiple axis, but with a carrier what? Avoidance. So the way how it works, so all right, so your station has a frame to send. Yeah, okay, your wireless node in here, okay, has a station has a data to send. So it will check if the channel is free, okay, and checking the channel is free, what we call the process carrier sense the carrier. What is the carrier right now? What is the carrier?
The radio waves?
The room, the whole world. There is no media. The carrier now is, the air. Okay, free air. All right, channel free. Is it a free? If it's not a free, then go back and try again. If it's a free, that maybe you are ready to send. So you have to wait for a time. This time they call it DIFs, okay, interframe, differentiated interframe system, I think. I forgot what it is. Let me check. Um, uh, Distributed interspace. It's a time, certain time you have to wait for it. Distributed interframe space, right? It will wait for a time. Then it will send RTS. What is RTS? What is RTS?
Ready?
Request to send. So it will send, this node needs to send data. So it will send a message to everybody, request to send. Request to send. Okay, everybody will know that I want to transmit. So if they know I wanted to transmit, what they should do? What they should do? If I tell you I want to talk, what you will do?
Well, we talk.
Huh?
They'll listen.
You will refrain from talking, right? Same thing.
Yeah.
This node will send RTS, request to talk. So what will happen to all the nodes listen to this? Will stop talking. They will not send anything. All right. Then they set a timer. Okay. They don't just want to give it a time until everybody knows that you want to send. They receive the signal. They stop talking at all. And then what will happen? Okay. Uh, this machine will receive clear to send received before timeout. So okay, it will receive from everybody clear to send. Oh, you want to send, request to send, clear to send. So when it receives a clear to send, all right, then it waits for some time, okay, and then it sends the frame. That's the transmission when it happens. Okay, that's when the transmission happens. Again, it waits for a time, and then it has to receive an acknowledgement, right? When you send the data, you have to receive acknowledgement it was received. If the acknowledgement received before the timeout, then you are successful. All right. So why we have used the RTS, request to send, and the clear to send? Why? For collision avoidance. Collision avoidance. I want to avoid collision. So before I start sending, I will clear the air. I'll tell everybody I want to send. So I send RTS, request to send. I wait until I receive approval, clear to send. You are clear to send. Then what I will do, I'll send the packet. All right. Let's say that you did not receive clear to send within the time. There is a timeout. What will happen? You failed. Nobody wants me to send. Nobody send me clear to send. False. So what will happen? You go in here and b plus b1 b plus 1 the back off variable. So you'll wait for a while. Then okay, then you check if it's not at the limit. You're gonna go wait for back off time, and you try again. And you try again by checking the channel is free. Free. If it's free, you send request to send. Wait until you get clear to send, and if you get it clear to send, you send it. You receive the acknowledgement. Great, then you're successful. If not, you're gonna try the process again until you finish. So that is the main difference between the two technologies. Okay, there is collision avoidance used in the wireless communication, and there is collision detection, which is used where? In the regular Ethernet. All right, clear so far? All right. So look in here what will happen in the CSMA CA. Okay, what will happen? So in here, so source and destination. This source would like to send to the destination. And these are the other nodes, like us. Let's us in the same node. If there is myself would like to send to Justin a message in his cell phone. So what will happen? I will wait for a period of time, call it DIFS, all right? Then I will send RTS. What is RTS? Request to send. Then the destination will wait for some time and will send what? Clear to send. You are clear to send, all right? And then you wait for a time, then what you'll do, you'll send the data, all right? So what will happen? What will happen? Okay, for those machines receive the RTS, the other machines, what they will do? They will be nav. Will be nav. No carrier sense. They will not sense anything. Okay, so the destination will hear it, and other nodes will hear it. Okay, the node is receiving it, will send it clear to send. The other ones, they will shut up. Basically, I mean, they don't communicate. All right. Then after that, acknowledgement will go back. Acknowledgement going back. Then it's a success. All right. So what we are trying to do in here, carry collision avoidance and nav. Okay, for the other nodes. Is it clear? Okay. All right, and the nav is the network allocation vector. Network allocation vector. If you want to take a look at the frame format, again, what is this frame format? This is the Ethernet frame format, but for the wireless. All right, it will have the FCS 4 bytes, like CRC for check for data integrity, and then the frame body, which is the data. Okay, and it's from 0 to 2312 bytes. And then you have 4 addresses: address 1, address 2, address 3, address 4. Why you have 4 addresses? Because you could have BSS to BSS, or you could have access point to access point. Usually, like, you have 4 addresses. All right. So let's say I'm communicating with Muhammad over my cell phone to his cell phone. So my cell phone will send the data to where? To the access point. And the access point will send the data where? To his access point. And his access point will send it to where? To Muhammad. So how many addresses we have there? 4.
Too far, yeah.
4. If Muhammad and myself in the same network, so my data gonna go to where? To the access point.
Your access point.
And from access point to him. So how many addresses we have? 3. If I'm using BSS, there is no access point. So it's gonna go from my address to his address. How many addresses are used? 2. So we could use 2 addresses, or 3 addresses, or 4 addresses. But in here we have to reserve for the 4, the worst case, that's 4. So we have address 1, address 2, address 3, address 4. Clear? So that's exactly what we'll have. We have 4 addresses in here, right? All right, so for addresses for transmission, okay. What else? Okay, so we have in here the FC, okay, the FC with the frame control. The frame control is like controlling everything. It's like the operation. The operation is here. It's 2 bytes, 16 bits control everything. So in here, for example, the protocol version, 2 bits. So how many protocol versions we could have? 2 to the power 2, 4, right? So there's different protocol versions. Okay, there is the type of information. Is it a management packet? And then it will be 0, 0. Is it a control packet? It will be 0, 1. Is it a data? It will be 1, 0. So what is the data in here? Is it a management, or is it a control, or is it a real data? How I would know it? From the type. Then I go to the subtype, okay, which is 4 bits. The sub byte 4 bits. Okay, so it will tell you different, but we'll see it in a second. Then now we have the to DSS, from DSS. Okay, this is okay. It will tell you, is it going to the access point, from access point. So this will will explain that. All right. And then in the more flag, when set to 1 means more fragments. Remember, when you have a longer packet, what you will do with it? You fragment it. All right. So the first one, it will have 1. That means there is 1 more. And the second one it has 1. That was 1 more. Until the last one, it becomes 0. That means this is the last one. So this is to tell you about the fragments. And then in here, the retry in here, when set to 1 means retransmission frame. Okay, so it's retransmission. Okay, the same frame, but because it failed the first time, it's retransmission. And then in here, something new, the power management. All right. Now, when you send the signals in the when you send the signals of the data, all right, there is a power. The more power the signal has, the more control. Some of the access points could control the power, how much power. So it will be longer distance, and there is a regulations for that. There is a regulations for that. All right. So that's for the power control management. Then you have more data, which is 1 bit. Okay, it means the station has more data to send. This is not the last data. There is more data. Yes.
Professor.
Professor,
Yeah.
You.
we
Yes.
didn't hear.
We can't hear you, Professor.
Me too.
Can you hear me now?
Yes.
Yeah.
Oh,
Yes,
okay.
yes.
So what is the last thing? Did you hear about the power management?
No, just the start of it.
No.
Okay,
Just
the
the
power
start.
management, when I was talking about the power management, so you know when when you send the signal, wireless signal, the more power you give it, it will go further. All right? But the problem, if you increase the power, what will happen? The signals will overlap. So each access point allowed a range of power, minimum and maximum. And these ranges are controlled by the government. All right? For, to avoid the collision and overlap and all of that. Okay. So power management in here, this element, it means the station is in power management mode. All right. There is power management is actually, this is not what I said. Power management is you know what will happen, the nodes will sleep and wake up, okay, to avoid depletion of the battery. And instead of keeping checking the communication all the time, sometimes they go in a sleep mode to save in the battery. So if they are in that mode, that means they are in power management, they could save that power, okay, to reduce the consumption of the battery of the wireless device. Then more data, that there is more data to send. We, all of us, we send, we don't use, but it's like wire equivalent to provide privacy for encryption. And then this reserved, not used. So this is the wireless frame as you see it in here. One more time, it's a little bit different than we saw before. Okay, for example, it has 4 addresses. The size of the frame body is different. It used CRC or FCS, that's fine. Okay, but this is the frame control, and it's like a operation room. It will tell a lot. What is this frame? What is the type? What is the version type? And different things. All right, so these are the explanation for these. You could take a look in here. All right, so we said in the type in here, like in here, that one here, type, well, just a second. In the type of information, it could be management 00 or control 01 or the data. Okay, so in here, this packet could be management or control or real data. So when it's 00, then when it's 00, it's management, right? And when it's 01, it's control. So here it says control frames. So the FCC, the D, the address 1, and address 2. In the control frames, shorter, we have 2 addresses, right? Okay, this is what the RTS. That is the, remember the RTS sent in here. Let me go back. The RTS, the packet in here sent, the way it looked like this. That's the RTS, request to send. Source address, destination address, that's it. And the clear to send or acknowledgement, it looks like that. Okay, it's just the destination. So in here, okay, let me go back in here. So in here, when you send RTS, so what you are doing, the source will send a packet, RTS packet to destination. It will tell the destination, this is my address, all right? And of course, it will put the destination address because you need to move there. Now, for the CTS, I don't need to put this address anymore. Just I put the source address. It's gonna go there, okay? Because it's directed to to speed up the process. So you'll have only one address. All right. So value of the subfields in the controller frame. Let me go back in here. Go back in here. So remember in here we said there's subtypes. There's type and subtypes for bits. What are the subtypes? All right. It will be request to send RTS or a clear to send or acknowledgement. All right. Otherwise, it will be a normal data. It's a whole protocol, fantastic. I mean, the people who designed these over years, they really made a great communication. You send the data, you have a header. The header has fields or subfields. If each subfield, every bit, each bit, it has a meaning. So 101 in the subtype means this is RTS. All right, it's an RTS, exact. Okay, so it's like a very nice way of working. Okay, now remember that we said in here we have address 1, address 2, address 3, and address 4. Okay, that's how it is. I already explained it for you. So if you have, okay, and we here you have in here, where is it? DS in here, DS and DS, to and from. So one bit, How many options they have in here? 0, 0, 0, 1, 1, 0, 1, 1. Right? Right? 4 options, right? So when I go in here, these are the 4 options: 2DS 00, 10, 01, 11. All right. So the address 1 will mean it's a destination. The address 2 means the source. The address 3 will be for the BSS ID, and then here is not used because they are part of BSS, same network. All right. If it's 01, address 1 means the destination. Okay, address 2 will mean the access point. So in here, like ad hoc, like me and Muhammad connected together. Okay, in here it's like there is an access point. So the address 2 will be the access point, and address 3 will be the source. Okay, in here is like receiving access point, the source, and the destination. And this in here, receiving access point, sending access point. There's 2 access points: receiving, sending, and destination and source. All right. So it's like everything mapped together. Every single bit in the frame in here, it has a meaning. Every single bit in the frame has a meaning, like a map. All right. So in the exam, for example, in the exam, in your test, right? I might give you a frame like this, right? And I will give you the FC in bits. I'll give you okay in bits. All right. And then I will ask you, tell me the story in here. What's happening? Okay, is this communication access point to access point, or node to node, or there is one access point or two access points? Which part you could check this from? To DS and from DS. All right. Then there is four addresses in here. You know what is the address of the source access point. You will be able to know what's the source of the destination access point. You know what is the address, of the mobile device and the other mobile device. From where? From where? From this, from here. All right. So understanding the map in here is a very important. In the exam, I will give you a frame all ones and zeros, all ones and zeros. Okay, and I will give you this. You don't have to memorize this, of course. I'll give you the map, right? I'll give you this table. 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 All right. I'll give you everything. And the only thing I will confuse. I'll give you zeros and ones in here. So what you will do? Okay, you're gonna go for the first bytes and you put a line here. Okay, then you go to the first 2 bytes, you'll make a line in here, and the next 2 bytes you'll make a line in here. 6 bytes you make a line in here, one in here, in here, in here. In here will be variable. Remember, it's from 0 to 2000 something. All right, so you'll not be. So you have to start from one side, from the other side. Then I could ask you, what is the size of the frame body? Right. All right, I will ask you. So you'll add. So 4 plus 6 plus 2 plus 6 plus 6 plus 6 plus 2 plus 2. Take it from the size of the whole frame. You will know what is the size of the frame body, right? All right. If I put in here 0, 1, what does it mean? If I put 0, 1. So you go in here to the map in here. 0, 1. Where is 0? 0, 1. So the first address is what? The destination address. The second address is a sending access point, and this will be the source. All right. So it's like a map. It's like a puzzle. You have the map. You'll be able to read it and understand it and all of that, right? Of course. I mean, all you needed to do is to understand how it works. That's it. All right. If I have to ask you a question in the exam, I'll give you all of these. Just use them. All right. If you understand what you are doing, it will be a piece of cake. All right. Of course, you need to learn how to deal with a binary and all of that. And for that, also, I'll let you use a calculator. No, there's no problem. I care about your concept, your understanding of how things work, how things tied up together, how they work, the protocol, how it work together. Quickly, there's two problems with problems. One problem called hidden station problem, okay, and the other problem called exposed station problem in the wireless. Let me explain them very quickly before allow you to take your dinner. All right, so look in here. Look in here. What is happening in here? So each node will have a range, right? You could not transmit to the moon. This cannot send signal to the moon, right? It has like area where it could send, right? So this is the area for node B, range of B we call it. And this is the range of C, right? And in between them, A. So A could receive from B, and A could receive from C. But C and B cannot communicate. They are not in the same range, right? All right. So B and C are hidden. B and C are hidden from each other with respect to A. All right. All right. So let's say now B would like to send to A, and C would like to send to A. So the B, okay, wants to send to A, and C wants to send to A. So what is the first thing we're gonna do?
Carrier sense?
Carrier sense. All right. So A, B will listen. Oh, it's empty. all right,
Mm-hmm.
and C is empty, right? All right,
Yes.
okay, but because it's empty, they could at the same time do what? Start sending at the same time, and the collision. They tried their best to avoid, right? They tried their best to avoid. But C does not see B, and B does not see. So, oh, let's listen to A. It's free. There is no collision. They start sending, what will happen? Collision. Why? Because B and C are hidden from each other with respect to A. Didn't see it? Okay. So how we saw, okay, so the clear to send frame in CSMA and CA handshake can prevent collision. We explained that before. So what will happen? That B, before it sends the data, what does it do?
Ready to
Sends the
send
request
data.
to send. All right. A received the request to send. What A does now? Sends clear to send, okay, to everyone. All right.
Yeah.
To everyone.
Okay.
So what does it say? A to everyone. I'm busy. I'm busy. I'm waiting for a packet to come. Right? So C will not send Y because C did not send RTS.
No, it's just going to receive, correct?
What?
It's just going to receive. Receive the packet from A.
Yeah, it will receive the CTS from A.
Okay.
Okay, but C did not initiate the communication with A. So this packet to C telling it what? I will be receiving some packet from somebody else, don't bother me. And A will send the CTS to B, and B already sent the RTS, it's yours. So go and send. All right? So A, it tries to tell everybody, don't communicate with me right now, somebody is in business with me. All right? That's what it is. Then also the exposed station problem. Okay, C is exposed, okay, to transmission from A to B. All right. So now, for example, A tries A is sending to B. All right. But at the same time, C could send to D, or D could send to C. Okay. But because they are in the same range in here, C, when it's exposed, because it sees the transmission, it will not send data. It will not send data to D because it thinks the whole ether is busy. While if C sends to D and A sends to B at the same time, there is no problem. They are in different ranges. So this is because they are exposed. Okay, C is exposed. All right. So again, use of handshake in exposed station problem. As you see in here, C is exposed to A's transmission. A sends RTS, okay. Then B sends a clear to send, all right. A clear to send. C it could easily send to D because it's not in the collision, but because it will send RTS, it will think that if it sends it, there will be a collision, and think there will be a collision, but there's no collision because D and C in a different domain they could communicate, but because C shares a domain with the other nodes, it will not be able to send. It will refrain from sending. All right. All right, so quickly, I mean, for the Bluetooth, I mean, you heard about by Piconet, okay, primary, and you have secondary nodes connected. This is a scattered net in here where you have a primary, multiple sessions, then a primary, secondary could be connected together. This is how the frame, okay, connected. Don't worry about it. So next week we'll talk about point-to-point waves, but let me take